Picture this for a second. You're the adversary. You've managed to breach a network perimeter, you've scraped memory, and now you are sitting on an absolute goldmine of stolen credentials. We're talking hashes, tickets, the whole shebang. But here's the thing. Having the keys isn't the same as actually knowing how to drive the car, right? How do you magically become that target user on the network without setting off every single alarm bell in the building? Well, welcome to this explainer on user impersonation, where we're going to decode the exact mechanics of assuming a digital identity.
Here is our roadmap for today. We'll start with 1, anatomy of digital identity, move into 2, passing the NTLM hash, then 3, passing the Kerberos ticket, 4, process injection strategies, and wrap up with 5, token impersonation and management. All right, let's dive right into section 1, anatomy of digital identity, the Windows Security Foundation. So what exactly are we talking about here? Formally, we're looking at MITRE tactic T1550, user impersonation. The adversary's core goal here is straightforward but absolutely critical, leveraging obtained authentication material to assume the identity of the user to whom those credentials belong. You have the material, now you need the access. For defenders, this is the exact moment an attacker transforms from an external threat into a trusted insider. To understand this, we need to introduce what I like to call the holy trinity of Windows digital identity. You have the Logon Session, the access token, and the credential cache. Think of the access token like a digital VIP pass at a concert. When a user logs in, Windows creates a Logon Session with the unique Logon identifier, or LUID. That session is tied to an access token, which basically tells local resources exactly what you're allowed to do. But crucially, that session also links down to the LSASS credential cache. That cache holds the actual secrets, like NTLM hashes or Kerberos tickets that you use to prove who you are to the rest of the network. Moving right along to section 2, passing the NTLM hash, the legacy approach. Let's look at how tools like Mimikatz actually pull this off. When an adversary runs the secure-lusa PTH command, they aren't just magically authenticating. No, Mimikatz is forcibly patching the stolen NTLM hash directly into the credential cache of a login session in LSASS memory. The real beauty of this from an attacker's perspective, they never actually need to crack the hash to get the plaintext password. They literally just hotwire the credential cache. Pretty wild, right? But here's the catch, and why things are changing in the real world. Pass the hash relies on NTLM, which Microsoft is aggressively trying to phase out. More importantly, patching LSASS memory, that is highly anomalous behavior. Modern endpoint defenses like Windows Defender are going to spot that from a mile away. And adversaries are strategic. They don't want to get caught. So they've been forced to shift tactics to pass the ticket, which leverages Kerberos. Because it uses native Windows APIs rather than actively patching memory, it is vastly stealthier, and it can even bypass protections like Protected Process Lite or PPL. Which brings us to section 3, passing the Kerberos ticket, the stealth alternative. Looking at the workflow, an adversary uses a tool like Rubius with the ask_tgt command. They supply a target user's AES key to legitimately request a ticket-granting ticket, which neatly comes back encoded in base 64. Now, if you look at a KList output, this is where it clicks together. It maps those cached tickets directly to a specific logon identifier, or LUID. Remember our holy trinity from earlier? The ticket is living inside the credential cache of one specific logon session. But wait, you can't just take a stolen ticket and shove it into your current logon session. If you do that, you're going to overwrite or clobber your own tickets. That could ruin the real user's network access and create a massive trail of broken services. So the optimal strategy, like we see with Cobalt Strike here, is using the make token command with a completely fake password. This is a brilliant move. It spawns a brand new empty logon session. Now the adversary has a safe, isolated container where they can inject that base 64 ticket without breaking the whole system. Okay, but this brings up a massive stumbling block for practitioners when they're first learning this. You've just passed the ticket into this new session, you excitedly type get UID to confirm your new identity, and wait, it spits back your old username. What on earth is going on here? Well, this reveals a really vital quirk in the Windows architecture. When you run a command like getUID or whoami, Windows pulls that information from the primary access token of the process you're currently running in. It completely ignores whatever alternate network credentials you just injected into the cache. Think of it like this. You essentially have a local face and a network mask. Locally, you are still the original user. But the moment you reach out to a network share, Windows uses the Kerberos ticket in the cache,
and your digital mask goes to work.
Let's pivot to Section 4, Process Injection Strategies, Hijacking the Address Space.
Instead of messing around with caches, what if you just hijacked a program the target user is already running? An adversary can actually inject beacon shellcode directly into a process owned by a different user. Because the payload now lives inside that process's address space, it automatically inherits their security context. Instant impersonation. However, the major gotcha you need to take away from this is that you absolutely must have a high-integrity session, like administrator privileges, to inject code into another user's process in the first place.
Finally, Section 5, Token Impersonation and Management, Stealing the VIP Pass. When you successfully impersonate a token, whether you created one with plaintext credentials or just stole it, command and control frameworks make it super obvious. Look at this interface. The user field actually updates to show the impersonated identity in brackets. You are, for all intents and purposes, visibly wearing the digital mask. Let's look under the hood of the absolute technical ground truth here. When an adversary types a command like steal_token, it isn't magic. It's exactly these 4 Windows APIs executed in sequence. First, open process, to get a handle on the victim's process. Second, open process token, to grab a handle to their primary access token. Third, duplicate token to make a usable copy of it. And finally, impersonate logged on user to actually apply that VIP pass to the adversary's thread. It's just a highly structured native OS interaction. There is a huge vulnerability for the attacker here, though. If you steal a token from a process and that target process suddenly closes, poof, your stolen token can just disappear. To solve this, advanced frameworks use a token store because the Windows kernel uses reference counting. If the adversary's token store holds an active handle to the token, the kernel won't delete it, even if the original process dies. This allows attackers to act like digital hoarders, showing, using, and removing VIP passes from their store whenever they please. And naturally, every good actor needs to know how to take off the mask, right? If you get stuck impersonating a user with limited rights, you absolutely need an exit strategy. The Rev2 self-command simply calls the native revert to self API. It drops the impersonated token and returns your thread right back to its original and hopefully higher privileged context. So we've seen how adversaries navigate the anatomy of Windows identity. We've watched them shift from anomalous memory patching to seamlessly blending in using native APIs for passing tickets and duplicating tokens. I want to leave you with this provocative thought. If an attacker is simply calling the exact same Windows APIs that the operating system itself uses every single day, how robust are your endpoint defenses at distinguishing a legitimate system action from an adversary wearing a stolen digital mask? It's a massive challenge for sure, and one that makes the whole cat and mouse game of endpoint detection incredibly fascinating.